Did you hear that? Or maybe I'm the only one who hears that. But anyway, it's getting recorded now. Any other questions? Okay, good. You heard it. You know, I'm not very good with reading and talking and other things at the same time. I don't know. Maybe I'm just not coordinated yet. But I wish I was better at reading questions. I'd really prefer it if you could, is just to turn off your mute and holler if you have any questions. So I'll take it that no one has any questions.
I think you said this before, but they will be recorded, right?
Yes.
Okay, thank you.
Yeah. And in fact, we're recording right now. And please, if I forget, just let me know so I can record these and everybody can benefit from any little thing that we might say.
So then, since we don't like have to come to the meetings from 9:35 to 11, does that mean we'll be fine if we miss, since some of us have to attend the lab on campus at 11:10?
Oh, absolutely. And that's another reason why I like to tape these and post them, because if you think you're missing some information, then you can review them. But essentially, what I planned this session for is kind of like an office hour. So if anyone has any specific questions, we have meeting times twice a week where you can air your question. Also, this time I would like to take, if anyone's interested, I mean, if everyone leaves and that no one has any questions, I won't do this, but I would like to start going over those PowerPoint notes and try to show you how I view them and maybe how I can extract some of the more interesting and the more important points of those PowerPoints and how they help you answer the homework. So for today, for example, after we're done talking and going over any questions, I would like to start taking a look at those notes, just to, you know, maybe the first 10 or 15 plates in the PowerPoints. And for kinetics, I think there's like close to 60 plates. So I just want to go over maybe the first 10 or 15 and take a look at those concepts, and then go to the homework and show, you know, what those homework problems look like and how you can use the stuff that is in the PowerPoint and of course your textbook to help you answer those homework problems. So I hope that answered your question. If not, just ask again. Anyone else have a question?
I know you said that we have like 35, did you say 35-hour window to take the exams? But once we start them, can we go back to it? Or is there like a set time?
That's a great question. Thanks for asking. It's going to be just like the homeworks, except you only get one submission before the deadline. And with the homework, like the exams, you can go through and read all the questions. You can take screenshots or whatever. I think some students were able to print them, but I don't know how to do that. And yeah, you can use all that time. You can even go back, and if you clicked a certain answer for one of the questions, you can go back and change it, and it won't count against you as long as you haven't submitted it. You get 2 submissions for the homeworks, 1 for the exam. Yeah, so if you want to sleep on it, like, you know, I'm thinking about this problem and I think I know the answer, and so I'll put it down, but you know, sometimes when you sleep on it, your brain processes information and you wake up and you're like, no, that's not quite right, and you go back and figure it out. I've done that many times as a student. Any other questions? Okay, so there's no other questions, we have 33 people participating here. That's great. And if you want, I can start pulling up anything from the internet, go over those notes, the PowerPoint notes, and maybe take a look at kinetics. What do you guys think? Okay, so yeah, you can come in and go. I don't take attendance or anything like that. So, all right, well, next thing I'd like to do is share my screen. Let's make sure before I do that. Okay, everybody's admitted. Waiting room 2. Okay. All righty. So can you guys see my screen?
Yes.
Okay,
Yeah.
cool. Thank
Yeah.
you. I'll get rid of that. I don't need that. And what I do need is the PowerPoint slide. So here is the first PowerPoint slide dealing with chemical kinetics. And I think that's chapter 12. Oh, that's Chica. Anyway, kinetics is the topic which tries to address how reactions proceed in terms of speed. So how fast do reactions occur? What do you think we would need to look at in terms of a reaction? What would be the important criterion to get a handle on how fast reactions go? Does anybody have an idea?
Temperature?
That's an important factor. Yeah. Awesome. Anyone else?
Hi, I would just say probably all the factors in the environment that are included, which could be temperature and all the different factors.
Yeah, that's true. Everything. And we are going to narrow down that list to just a few things. But when we talk about the and so here's the next slide. And you guys are right. This is just the 5 main things which really incorporate what you said. Number 1 is the nature of the reaction. You know, what kind of reaction are we dealing with? Are we dealing with an acid-base neutralization reaction? That's going to have a different rate than, say, an explosion, a combustion, or a radical type of a reaction, which happens very quickly. So you'll know the nature of a reaction when you know what's reacting. So number 1 is the reactants are really important, and it's kind of obvious, but we just throw that out there. So everybody, yeah, sure, that's a no-brainer when you think about that. Of course, the reactants are going to dictate how fast reactions go. And then some of the other important criterion that we're going to get into and try to model mathematically come next, like the reactant concentration, the temperature, and action of a catalyst. For the last one, surface area is just a physical state, so we just mention it. So what do you think about surface area as far as reaction rate? And anybody have any feelings about that and how it affects reaction rate?
Probably
That's probably
the more that the chemicals have access to each other, the more they'll react.
Absolutely. So that's kind of a pretty apparent way that you would think about it, and it comes out that way. So the more the surface area, the faster the rate of reaction. And this is sometimes a topic of a chemical demonstration, like if you went to science night, maybe in elementary school. They had this demonstration called dragon's breath, where they take this lycopodium powder and they try to burn it with a Bunsen burner, and it doesn't not light at all. But if you aspirate this powder through an aspirator, a small orifice, and it blows it into small particles, and then light it, it just blows up. And this is a problem whenever you have a work environment, such as farms have those large grain silos that aspirate the grain in there. And sometimes if a spark is found in there, the whole xylem can blow up. And so you might see that demonstration done like at a science night, but on a smaller scale. The things that we concentrate on in this class are the numbers 2, 3, and 4. So that's what we're really going to look at. And I think that most people sitting there could probably tell me how a reaction rate would change when you change a reactant concentration. What do you think? What happens to the reaction rate, say, when you increase a reactant concentration?
Probably increases the rate.
Yeah, absolutely. And that's not always true, because you can put in what's called a retardant, and it could actually slow down the rate of reaction. But in general, that's true. How about temperature? Increased temperature, what happens?
Increased rate.
Yep. And if I add a catalyst, what happens?
Okay.
Yeah. See, you guys know this stuff already, right? Well, you kind of know the effects, but what we're going to do is we're going to try to understand these effects conceptually, and then we're going to apply mathematical equations to these concepts, which will allow us to quantify the effect. You know, if I do this amount of change in the concentration, then what is the effect on the rate of the reaction, right? So that's where we're heading. And so just like every other thing that we learn, we crawl first, then walk, and then run. So we're just, going to the basics, trying to understand what we already know, and then build on that. And that's pretty much the view you should take from Chem 200. Chem 200 is going to give you a lot of the background to understand many of the things that we talk about in Chem 201. But on the other hand, in Chem 201, we're going to be thinking about and making models for stuff that you probably haven't seen yet in chemistry. So the second semester chemistry is a lot different than the first, because the topics that we discuss, like kinetics, they haven't been discussed previously. All right, so the first thing we go from there, so we have our main topics that we want to look at and their effect on kinetics and the speed of reactions. We want to be able to build mathematical models. So we have to go back and say, okay, we're studying reactions. What is it about reactions that we can measure that will help us understand something about the rate of a chemical reaction? So if you think about that for a while, you'll say, oh, well, geez, you're going to have to know something about the amount of reactants and products during any given time, right? So just like we talk about our rate of, say, running, if I wanted to talk about the rate of speed of a person running on a track field, then I'm going to look at some of the things that I can measure about that person and their movement, namely the distance they travel in a given amount of time. So all we need to do is understand, instead of talking about a person running in a track, we're talking about a chemical being consumed if it's a reactant and being produced if it's a product in a given amount of time. And that is the basics of chemical kinetics. And did anybody have a question or anything? No? Okay. If there's a question, please just blurt it out. Don't worry about interrupting, because I'm not reading anything that you guys are writing. I guess I could, but it's kind of distracting. So if you really want to ask a question, please just go ahead and interrupt me. All right. There's so many things that are distracting. Let's see. Okay, I'm just reading over this. I don't see anything that I have to address. All right. So back to trying to understand chemical reactions in terms of rates. So an obvious mathematical concept or construct to apply to chemical reactions is what we call the average rate. And you have to be familiar with these mathematical symbols that we use, namely the delta sign. Does anybody know what that delta sign means?
Change of.
Yeah. So in math, delta, the big delta, refers to change. So we're looking at how does the change of moles of B, how does that look in terms of the change in time? So this delta, we have to remember from math that it's always a final minus initial. So if we look at the delta t, for example, the final time minus the initial goes here in that mathematical expression, just like if we were to look at the rate of speed of some human running would be their change in distance over change in time, right? Like miles per hour or meters per second. So this rate is similar to that, but we're looking at changes of the number of molecules, whether it be a product, in this case B, or a reactant, in this case A, for some simple reaction. Now, the delta T is really easy because that's when you start and stop the stopwatch. So in lab, you'll mix two reactants together and you'll start your stopwatch. So the initial time is 0 often. So this is always taken as 0 for time. And the final is when you stop the stopwatch. So we can get a handle using just this very simple idea, a handle on the average rate of any reaction. Okay. We can, oops, I have to go back one. We can plot how those numbers of moles change in time, and you can see how A relates to B. So if we start out with all of A, so say we have 1 mole of A and 0 of B, as time goes on, B is going to increase in concentration, and at the same time as A is decreasing. And since they're in this reaction 1 to 1, so our stoichiometric coefficients are both 1, then the amount that A goes down here, which is 0.24, is the amount that B increases. Okay, so it makes sense that we can follow the amounts in time for any chemical reaction. All right.
I
So,
have a question.
yeah, shoot.
Oh, so what you just explained right now, does that explain why it's a negative, why the average rate is equal, like where it has a negative sign in the previous slide?
Yes. Thanks for pointing that out. Let's go back to that previous slide. You were wondering why there was a negative sign up here. Brilliant. And you figured it out. Okay, so the rate at which I lose A is going to equal to the rate at which I'm gaining B, because the stoichiometric coefficients are 1-to-1. For every one A that I lose, I gain a B. Now, because the way that we define delta as final minus initial, the concentration of B is increasing in time, so the final is going to be larger than the initial. Now, the opposite's true for A. A is decreasing in time, so for every A that we lose, this delta final is going to be less than the initial. And so this delta up here is going to be negative. To make these equations equal, we have to get rid of that negative sign by sticking in that negative there. Yes, so thanks for pointing that out. That was a important thing to point out.
Thank you.
Mm-hmm. And any other questions? Okay, good. So this slide here just asks you to go back at that plot and see if you can fill in some numbers and understand what's going on. So I think you can do that, or I'm going to give you a shot to do it on your own when you study these. All right, the next plate says, well, it doesn't say this, but the important thing about this plate is that we're not going to use moles over time. And it's just a practical reason why we don't, because when we go in the lab, as you know, from previous experience, or maybe you don't, depending on if you took a lab that met in the lab. But if you did, you would see that most things are not measured in moles. If you go under the hood and you grab a reagent bottle, the units are almost always units of molarity, moles per liter. So instead of doing rates in moles per time, oftentimes what we do instead in chemistry is use molarities per time, how the concentration changes in time. And that shouldn't be too much of a problem, I don't think, because that molarity unit is the same as the moles unit, except now we've added in a volume, which is in liters. And that's just a constant most of the time, because when you mix two beakers of reactants, say you got beaker 1, beaker 2, and you have A in here and B in here, and you want to mix them all together, then you're going to dump them in. So you have A and B, your two reactants. This volume doesn't really change very much or at all. So thinking of this reaction rate in terms of moles per time versus something like molarity per time. Well, molarity, that's just moles per liter, and liter's just a constant, because this volume doesn't change pretty much when, after you mix your reactants. So I think that's the argument, and that's what we're mainly going to use is molarity units in our rates. So that talks about it here a little bit. And then we have some data that you might be taking it in lab. It could be a Beer's law type of experiment where you can track the concentration of, in this case, it looks like a reactant right here, and how its concentration changes in time. So how does this look, the concentration changing in time? What's happening to that? Is anybody there?
It's getting weaker.
Yeah, so the time's getting bigger, right? And the concentration is opposite, or it's going down, right? So the concentration of our reactant's decreasing in time. And that's what should happen, right? Because it's getting consumed. Now, the average rate in molarities per second. So I can calculate each one of these rates by just taking the change in the concentration, right? And the change in time and plugging it into that equation. And for each one, I get a value, right? So that's the average rate of reaction. What's happening to the rate of reaction as time goes on?
Slowing down.
Yeah, look at that. It's slowing down. Does that make sense?
Yes.
Why? You knew I was going to ask you.
Is it because
Go ahead. Sorry.
like the concentration of the reactant is going down?
Yeah, and that's what we said in the beginning, right? That first slide we said, oh, well, the rate of a reaction is inversely proportional to the concentration of a reactant. So as that concentration decreases, I would expect the rate of the reaction to decrease. And that's what we see. And this is true for most reactions, not all, but most reactions are like this. All right, good. I think we extracted most of the learning material out of that plate. Now, sometimes people want to talk about instantaneous rates as opposed to an average rate. So what's the difference between an instantaneous rate and an average rate? Well, I think most of you know the difference is that you're just talking about one instance in time and how the rate is at that particular instant, as opposed to over a period of time. And that's what we mostly are interested in, is instantaneous rates. So how would that look as far as on a plot and mathematically? So here I have the plot of that previous page. In this case, I have the concentration of that reactant in the y-axis and time along the x. So again, it shows you how the concentration changes with time. It goes down. It's a reactant. It's getting consumed. And if I were to calculate average rates, then I would take the difference between these points in concentration and time. So I would take the change in the reactant, I'm just going to call it B, and I would divide that by the change in the time that correspond here in the time column versus the reactant concentration. And I can find the averages. But what if I don't want the averages? What if I want the instantaneous rates at those particular points in time? What do I have to do then? Anybody know?
Derivative?
Yes. So there are some math geniuses out there who know about derivatives. But guess what? This class is a non-calculus based chemistry class, so you don't have to worry about it if you don't know. So don't be frightened because we don't have to know about derivatives. But people who do know will understand that what we want is we want to find out the this ratio in the limit where delta t it approaches zero. It's very tiny where that just a little tiny increment away from where it was. And that's a job for derivatives. But since this class isn't calculus based, how can we do it? Well, some of you may know that you can calculate an instantaneous value by taking your data and plotting it. You fit it to a line and take the derivative of that line at the point. Another way to do it, though, is graphically, and that is if I want, say, to find the rate right at that initial concentration, then what I would need is to find the slope of the tangent to that curve that touches only at that point in time that I'm interested in. And you can see, I think, graphically, that the slope initially, when we have the highest concentration, is different than a slope, say, further down in time, where it touches, I don't know, right there at about 700 seconds. Can you see the difference in the slopes of those tangents? i.e., which one has a higher slope?
The one that's more to the left.
Yeah, the initial one. And so this goes hand in hand with what we just said. The rate of the reaction decreases, and so does the slope. And guess what? The slope of these tangents have the right units. Change in y over change in x. So the rate has units of molarities per second, and that's what we want. So if we were interested in finding instantaneous rates by plotting experimental data and finding the slope of the tangent to that data at the time of interest, we could do it. Okay, so that was the purpose of this slide, to help you guys connect what we're doing to calculus and derivatives and stuff, if you know it. And if you don't, it's okay. There's other ways around it. Any questions on that? All right. Let's move on. Okay, sometimes we're going to need to, or it's advantageous to be able to talk about the rate of consumption of any of the reactants as compared to the rate of production of any of the products. And so we need to understand how that stoichiometric coefficient in a balanced chemical equation is involved in relating those rates. So, for example, I have this reaction right here. And if I want to talk about the rate of that reaction, I could talk about maybe how fast I'm consuming one of the reactants, or maybe how fast I'm producing one of the products. But you have to remember that the rate of consumption and production of any reactant and product are related to each other. How are they related to each other? Well, through what we said before. For example, if the species in the balanced chemical reaction is a reactant, then its concentration is going to be decreasing in time. So all I would need to do is insert that negative sign there, and then I can see what the relationship would be to the production of any of the products. So hopefully you can see that. Now, this particular example reaction has stoichiometric coefficients that are all 1. What happens when they're not all 1? And there's a lot of cases where they're not all 1. How do they relate then? Well, down here, it gives you the relationship. And this idea here will help you answer the questions in your homework and also for the exams and stuff. If you're given the reaction rate of any one of the species in a balanced chemical reaction, it could be a reactant, it could be a product. If you're given that, then you can figure out what the reaction rate of any of the others are, as well as the overall reaction rate, because they're all related. So here, let me show you. Here's some generalized reaction, okay? And it has stoichiometric coefficients, which are the little letters, and the reactants and the products are the large capital letters. So now, the next line shows us the rate, this is of the reaction. And this is a kind of a definition. So I can put in 3 lines here. So the rate of the overall reaction is related to the individual rates of consumption or production of reactants or products. The first term here shows how the rate of consumption of A is involved in this relationship. This next term shows the rate of consumption of B. And this following term is the rate of production of C and the rate of production of D. You see how the stoichiometric coefficients are involved as kind of weighting factors. And this overall relationship will allow you to answer those problems in the homework. For example, if they say, oh, the rate of production of D is 10 molarities per second. And then they say, well, what is the overall rate of the reaction? Well, that's easy. All I need to do is take the stoichiometric coefficient D and divide it into the rate of production, which is 10, and I get the overall rate of the reaction. Or if they ask instead, the rate of production of D is 10 molarities per second, what is the rate of production of C? Then I can solve for C right here. All I need to do is take that 10, which is this value here, divide it by D, multiply it by C, and solve for what I want, which is the rate of production of C. Any questions on that? What I'd like to look at is the next plate, and it kind of takes this generalized formula and defines a little bit more of those things that I just glossed over, the definitions of those ratios. And so this ratio here is the rate of consumption of A and so forth. And it also shows you how to relate to of them. And then the slide after that kind of gives you a specific example. Okay. So if we look at this slide, it says, all right, let's apply that generalized rate equation to this specific example of 2HI reacts to form hydrogen and H2 gas. All right. Now, if a problem says, for example, that the production of I2 is, let's use our example, 10 molarities per second again. right? Then what is the rate of consumption of A? So I think most people can see that. They just need to look at that relationship and say, oh, here's how they relate. And I got that from using the generalized equation. I just applied it to that reaction. And it says H2, I'm sorry, I2 is 10 molarities per second, which is right here. This is 10 molarities per second. And what's the consumption of A? I mean, not A, I mean HI. That's the reactant. Sorry about that. I need to solve for this. Okay, so I want to solve for that. So I'm going to clear both sides. I need to multiply both sides by 2. So that means delta HI over delta T equals 2 times 10, which is 20 molarities per second. Any questions on that? Where I got that? All right, then let me ask you this. Given what we just said, what would the rate, the overall rate of the reaction be? Anybody have a guess? Is that, are you guys still there?
Is it 10?
Yeah. So if I want to calculate the rate, and I know that this is 10, then yes, you're absolutely correct. It's 10 molarities per second. So you see that anytime one of your species, whether it's a reactant or a product, has a stoichiometric coefficient of 1, then according to this definition, its rate of consumption or production equals the overall rate of the reaction from this definition. Okay, does everyone see that? So anytime yeah, go
Sorry.
ahead.
Is it okay if we go over another example
Oh,
to go through
absolutely.
the process
Yes,
again?
yes. Yeah, we can do that. And before we do that, before we go to another example, I just wanted to ask if there's any questions on what we said here. And if not, then we'll go to another example. But also I have just a question while we're here for you guys. Sometimes you'll be asked, which of the species here in this balanced chemical reaction has the fastest rate of change? And of course, I want to do a follow-up question, which is, why do you think it's the fastest? So is HI, the reactant, is that changing its concentration faster in time than the production of H2 or I2, or vice versa?
Yeah, it's being consumed faster because there's 2 moles of it.
Absolutely. So that has the fastest rate of change. So if I'm going to relate that to the other ones, their rate of production, and I know this is the fastest, then doesn't it make sense if, say, delta A over T represents HI, doesn't that make sense that I have to scale it by the largest coefficient to relate it to the other ones? Because it's changing twice the amount that the other guys are changing. It's twice as fast. So that's kind of a rationalization for the form of this overall equation that relates the rate of change of the reactants and the products to themselves, as well as the overall rate. So if it has a larger stoichiometric coefficient, its rate's going to be changing faster. So that stoichiometric coefficient has to be used to scale the rate, which is this ratio, in order to relate it to the others. So that's just something you could think about. It's in the background, and I think it's important to understand. All right, but now what I want to do is to go back and let me see. I just want to insert a new slide. Yeah, here we go. Okay, so let's just think about that equation and make up a reaction. Let's blow something up. C2H6 plus O2 goes to CO2 and water. Okay. So the first thing we're going to need to do is balance this equation. So you guys, you have to balance using your Chem 200 knowledge, and we used to call this balancing by inspection. So I see that oxygen in this term is all alone, so I'm going to leave that for last. If I put 2 here, then that balances my carbons. I need to balance my hydrogens, and so I could put a 3 there, right? That leaves my oxygens, and I have 4, 5, 6, 7 oxygens on the left. So all I need to do is put a 7/2 here, and that's balanced. And that's great for people who are accountants. All the numbers are set. You can do your stoichiometry problems and you'll be fine. But physicists and chemists don't like this because you can't have fractional molecules, because if you broke up a molecule, then it wouldn't be that molecule, it'd be something else. So chemists and physicists, they complain about that and say you got to multiply through by 2. And so this 1 here becomes a 2. This becomes a 7. This becomes a 4. And this is 6. Now it's properly balanced. All right. Now I have this balanced equation. And my question to you is, which one of the reactants or products has the largest rate of change?
Oxygen.
Oxygen. Brilliant. And the reasoning behind that is that it has the highest stoichiometric coefficient. So it takes 7 oxygens for every 2 ethanes. And it takes 7 oxygens for every 4 carbon dioxides that are produced. And it takes 7 oxygens for every 6 waters. So it has the fastest rate of change. So when I use the equation that we just introduced on relating these rates of change to the overall rate of reaction, I'll just put rate of reaction, then I see that it's going to be 1/2 times the change in C2H6. And I have to put a negative sign in there because this is decreasing in time, and that delta is going to be negative. So a negative times a negative makes a positive. I have 1/7 for O2, sorry, delta O2 over delta T, 1/4 delta CO2 and 1/6 delta H2O. And I have to apologize for my handwriting because I'm writing in the air. I can't rest my hand on the computer or it just messes it up. So sorry, it looks really sloppy, but I think you can read it, right? So do you see where that came from? I just applied that generalized relationship. Everyone see that?
Yes.
Yeah. Okay, cool.
Yep.
All right. No questions on that. Now, some of the questions will be like, okay, the rate of the reaction is 5 molarities per second. What's the rate of consumption of, I don't know, ethane, right? You can answer that question. Or it'll say the rate of production of CO2 is 3.5 molarities per second. What's the rate of consumption of oxygen? Then you can answer that question because you can just solve this generalized rate equation, which allows you to relate the overall rate of the reaction to the rate of any one of the species. Now notice these rates don't include the stoichiometric coefficient. The stoichiometric coefficient is used to scale those rates so they can relate to the others in the balanced chemical equation. And it makes sense that the species with the highest stoichiometric coefficient has the highest rate and therefore should be scaled by the highest factor, divided by the highest factor to relate to the other rates. And so that's what I was saying before. And this is another example of it. Now, anything goes in the problems. So what I was saying before is like, if they say, okay, anybody out there, you can pick it. The rate of which species you want to use or whatever. The rate of
hydrogen,
I'm sorry, what'd you say?
carbon.
Okay, you want to do the carbon dioxide?
Yes.
Okay, so the rate of, it's a product, so I would put production. Production of CO2 is, anybody want to make up a number?
6.
Okay, thanks. 6 molarities per second. Okay, what is the rate of, okay, which other guy you want to pick on now?
Ethane.
Okay, what's the rate of consumption? Of ethane. That's C2H6, question mark. So to answer this question, you just have to relate those two, and I can pull them out of that generalized equation and say that minus 1/2 times delta, delta goes on the outside, C2H6 over delta T equals 1/4 delta CO2. And I want to, oh, no, sorry, I want to solve for this term because this delta C2H6 over delta T, that is the rate of consumption of C2H6, right? So this is what they gave me, or you gave it to me, 6. So my answer would be for this 2 over 4 times 6. And there it is. Does that make sense?
Professor, sorry, I think I missed it where the coefficient came from for the number 4.
Uh-huh. Yeah, it's from the balanced chemical equation up here.
Oh, okay.
Yeah. So that's how these stoichiometric coefficients are involved, and that can be easily missed, like back here and here. You see where I first introduced that equation back here? These stoichiometric coefficients are defined here. So take some generalized equation, right? That little a is the stoichiometric coefficient, and that comes into here, this play in this equation. And b goes here, and c, that stoichiometric coefficient goes down here. Does that make sense?
Yeah, I didn't realize that you like balanced it in your head or something before going on to the right portion.
Yeah. Yep. So no, we balance chemical equations like you did in Chem 200. It's called balancing by inspection. You just change the stoichiometric coefficients until everything's balanced. This is going to be different, by the way. You're going to learn a new method for balancing called balancing using the half reaction method specifically for reactions involving redox, reduction oxidation. And we'll get to that later in the class. But anyway, I think we went through a good amount of material. And we could go on with our discussion on more topics. But I think I'm going to stop here now, and I'll just wait for people in case they have any questions or they want to go over something else until tomorrow, if you have an opportunity to come by and discuss some more of these notes.
I have a quick question, Professor.
Yeah, sure.
So I noticed on the rate of consumption, you kind of leave off the negative. Is that just because the negative denotes that product is being consumed?
Yes, absolutely. So the words are important too. So when you talk about consumption, like we did here, that takes care of it. You know that it's decreasing in concentration, so you don't have to put the negative in.
Cool.
Yes.
Cool.
So
Makes sense.
yeah. So thanks for pointing that out, because sometimes you want to say that in words, and sometimes you want to do it mathematically. So if you say it in words, consumption, then that implies that it's negative. You're decreasing in the amount. Or I can say the rate of reaction. Another way to say this is the rate of reaction of ethane is minus 3 molarities per second. Okay, thanks for asking.
Professor, just to clarify, is the 2/4 from the denominators of the other two fractions?
Yeah, so what I did was I just took out that one piece that involved the answer to the question. They gave me, or you guys gave me, the rate of production of CO2 and asked for the rate of consumption of ethane. So I just pulled out these two terms, the ethane term and the CO2 term, because they're all equal. All of these are equal to each other. And so I just pulled them out and put them down here. And that's what I started with. And I said, okay, to answer this question, what I need to solve for is this rate of consumption. So I need to clear the terms. I need to get rid of this minus half and bring it over to the other side. So I multiply both sides by 2, and that's where this 2 came from.
Thank
You
you.
see? Yeah.
Hey, I'm in class. Zoom class. Yeah, I hit you back, boy. All right, come up.
Okay. Any other questions on this or anything?
I forgot if you mentioned this before about the PowerPoints, but will they be like, will they be sent or do we just access them through the videos?
The PowerPoints are in Canvas. So I can show them to you right now, actually, if I share my screen again.
Okay, thank you.
Yeah, we can take a quick look through the homepage. Okay. So here is the homepage for the class, and it's the same for Tuesday and Wednesday. This is where you guys entered into the Zoom meeting, and right below it, chapter 12, kinetics, there's the PowerPoint right there, and here's the homework. And then the next chapter is right below that. There's the PowerPoint, and there's the homework, and so forth.
Okay, thank you.
Sure. And I didn't mention this, but while I'm here, the discussion area, I have that divvied up into topics. So if you guys have any questions and you didn't get a chance to ask them now, then you can post them under these topics. The first one is for the final and any questions of a general nature. I should probably redo this and make this one first. This one down here, exam 1, chapter 12 and 13. If you have any questions on the stuff that we talked about today or for the first exam, then you can post them here. And exam 2, exam 3, and then final. So that's just another source for you guys to get some help.
A question, Professor. I missed the beginning part of class. So, is there a book for the course? I still have to look through the syllabus and stuff. But do we have? I'm a VA student, so just trying to figure out, how I'm gonna get my books and stuff.
Yes, there is a book. It's the Zumdahl. It's a general chemistry book, and
Okay.
yeah, and it's in the syllabus, so you can look for the name there. Now,
Okay.
the edition that I used to get the test bank and form your homework and tests from is the 10th edition. It's the latest edition, but that edition is going to cost you a lot of money. And I don't see any reason why
Okay.
you can't get away with an earlier edition if you don't have the cash. I don't know exactly what the differences are, but usually they're fairly minor differences.
Okay. So we need that book. So we need the book to do the start the homework. So we will need a book to do the homework starting out.
No.
Okay. All
You
right.
can use any general chemistry textbook that's of a second semester college non-calculus based course. And so there's a lot of general textbooks that go over the same topics that we do, slightly different flavor or different examples. Like we used Silberberg for a long time here. Before that, Brown and LeMay. There's Tro that they use, I believe, at Miramar. And all of these books are good standard general chemistry textbooks that you can look up information. The reason why we require you to have that, at least one textbook, is because you're going to need sometimes to look up some definitions or some general concepts. Like if you don't understand a definition from the PowerPoint, then you can look it up in the textbook. And if you still don't understand it, then you got to ask, you know?
Okay, all right, thank you. And one last question, Professor. I see Tuesday and Wednesday, 9:35. So is the class, we just meeting for Tuesday for lecture 9:35, or is Wednesday as well? Or is Wednesdays just like a session for people who need help?
Yeah, Tuesday and Wednesday is just like a session for people who need help. And so, yeah, both of them are non-mandatory. They're just extra on top of the other stuff just to help. And I plan to tape them, and I plan to post them in that Zoom area where you enter into this Zoom meeting. I'm going to, right on below that, I'm going to start posting these with this video today.
Okay, just make sure, but Tuesday is our main lecture day, is when you're lecturing, and that we really got to be there, right? Just trying to make sure.
No, there is no main lecture day. You don't have to be there on Tuesday. I don't take attendance. It has nothing to do with your grade. This is just for help.
Okay, got it.
All right, thanks for asking that question, because I think a lot of people were really wondering about it.
Yeah, okay. All right, thank you.
Sure.
But on Wednesday, you won't go over any new material, right? I'm just trying to make, just make sure.
Yeah, I may go over new material, but I may go back and do all the stuff that we talked about today. There's no limit. All the material that you need for the homework and the exams are right here on this main page. All right. So I think we just went over that, right?
Yeah, yes, sir.
Here's the kinetics PowerPoint and the homework. So in theory, there's students who don't need to come to any of these or ask any questions. They just go to the PowerPoint slides, they read them, they take notes, they look up in the textbook, they understand it completely, and they ace their homeworks and their exams. In theory, it's possible never to come to any one of these and do well.
Well, I'm not that person, but I appreciate it though.
And neither am I. I was never that person either. I always kind of were like envious of those kind of people.
Hey, if you got it, you got it. I'm just not one.
Yeah, me either. I got to work for it.
Yes, I'm here. Awesome. Thank you. Thank you very much, Professor.
Sure, anytime. Okay, so that you were just looking at the ceiling of my office for all that time. Oh, so this is kind of all new to me, new computers and things and getting online, and I'm just figuring it out and trying to do the best I can, and I expect you to do the same. And so we'll just have to help each other through this. So, any other questions for you guys?
Professor, since you said that the book is going to be available, like we could use basically any introduction book. Is most of the information for this class going to be on the PowerPoints then?
Yes, the main content is going to be on the PowerPoint, and you can get information for any good second semester college chemistry textbook. Now, who defines whether it's good? You better ask me, or it's got to be one of those books that I just mentioned: Tro, Silberberg, Brown, LeMay, Yang, I think, has one. Yeah, in that category. So it's not just any. You can't use a Chem 152 book and expect to get the same material. Any other questions?
But most of like the homework questions we can answer off of the PowerPoint, right?
Yeah, you want to take a look at the homework?
Yeah, yes,
Yeah, come on,
please.
let's take a look at it. See what it looks like. All right. Let's get rid of this. All right, so when you open your homework, it's going to look like this right here. And question 1, the average rate of disappearance of ozone. So ozone is this first molecule, O3, and it's forming oxygen, O2. So its rate of disappearance is this number in atmospheres over a time interval. So instead of molarities per second, they're using atmospheres per second. But okay, it's all gas. What's the rate of appearance of O2 during this interval? So we just introduced that overall rate equation that helps us relate those two. So the thing that I want to do in order to answer this is, let me see. Move that here. So what I want to do is I want to apply what we talked about today or earlier and look at that reaction. It's always tricky for me to write on this. Here I go. Hopefully it's going to be good. So the rate of reaction equals minus delta concentration of O3, that's ozone, over delta T. And I have to put a 2 there. That equals the rate of production of oxygen. And I have to put a 3 here, right? That's how they relate. I learned that from the PowerPoint. They're telling me that the average rate of disappearance of ozone is this amount. So that's this ratio right here equals 8.76 times 10 to the minus 3. And what they're asking for is the rate of appearance of oxygen. So they're asking for this. That's what the question wants. So I know now that all I need to do is solve for that ratio. So that would be, let me call that the rate of appearance of O2. Call that, that's what this ratio is. That's going to equal the rate of disappearance. That's this ratio right here, divided by 2. So it'd be 8.76 times 10 to the minus 3, divided by 2 and multiplied by 3. Because I just took this relationship and I solved for this guy. So I had to clear that 3 by multiplying both sides by 3. That's where this came from. And this 2 over this is the rest of this up here. Is that clear or is that confusing?
Clear.
Yeah, that makes sense.
Okay, awesome. And so you're just going to go through that homework and let's take a look at the next one. They give you a balance equation at a particular time. They give you the rate of consumption of bromide. That's delta concentration of Br minus over delta T. That's the rate of production. I'm sorry, the rate of consumption of bromide. They give you that value and they ask you for the rate of production of bromine, Br2. So you have to use those stoichiometric coefficients again to find your relationship. The next one, which is possible rate law. We haven't talked about rate law, so that's all you can do so far, unless you go and try to read on your own, and maybe you can do it. And maybe you don't have to show up to any of those lectures and ask any questions and get that. But we haven't talked about rate laws yet. So,
I have a question about the homework.
okay.
Since we have 2 attempts, once we submit it once, are we gonna be able to see what questions we got wrong, or are we just gonna get a score?
I believe, and you can correct me on this, I believe it will tell you which questions you got wrong. And if it doesn't, let me know so I can flip a switch or something. But I have it set up to show you your responses.
Cool, awesome, thank you.
Yeah,
Professor,
sure. Yeah.
Professor, for question number 1, I punched in the numbers on my calculator, but I don't see on the multiple choice. Is my math wrong?
Yes. I did this one. Now I'm going to tell you what I think you may have done. Check out these factors of 10. They're all to the -3. So you might have to move your decimal point around.
Okay. Yeah, I got 2 decimal places.
Okay, so this one has 1 decimal place. This one has 2, 2. This doesn't have any here, and this has 1. So you got to fix your value so it has 10 to the -3 multiplied by it.
Okay. Well, thank you.
Yep. Any other questions? No? Well, I'm just going to hang out here until everybody leaves, and then I'm going to stop. I think yeah, go ahead.
Sorry to cut you off, Professor. Is the exam the same format as the homework?
Yes.
Okay.
So that
Have a
means
nice
that
day,
for
Professor.
the
Thank you.
homework,
Yeah, okay, guys. Anytime, let me know if you have problems. I'm just going to hang out here in case anybody wants to talk to me about anything.
Hi, Professor.
Hi, Melissa.
I'm so sorry. I came in late. I didn't realize we had a Tuesday meeting as well. And I apologize if you already said this. But just to make sure, Tuesdays and Wednesdays don't count towards our grade. They're mainly for if we have questions or and you'll review some things.
Yeah, that's absolutely correct. And it's okay. We're going to be reviewing a lot, I
Okay.
think. And that's how you learn stuff. You go back and redo it. So on Wednesday's gathering, I'd like to recap what we talked about and see if there's any questions before I go on to any new material. Plus, I'm going to post this, and that way you can slow it down and rewind it and stuff like that.
Okay, perfect. And then all of our quizzes, they're not like during class time, right? These are just gonna have separate due dates. I think if I looked at that one correctly, it's due like March 7th or 8th or something.
Yeah, so the kinetics homework is due on the 14th of February. And that's a Sunday night.
Oh.
I have the schedule right up here, but the schedule's in Canvas. Okay.
Perfect. Okay, yeah, I just want to make sure.
Yeah, and I also have the schedule here. It says that the equilibrium, the next chapter, is due the 21st. So you have 2 submissions before then, and you get the highest of the 2. And then exam 1 is going to be released on Saturday, the 6th of March by 11 a.m. I usually release it earlier than that, but by 11 a.m. it's going to be released, and it's not due until the next day, the 7th, by 12 p.m. And it should take you maybe 2-3 hours to do max, but you have 35 hours to do it and fit it in whenever you can.
Okay. Okay, perfect. All right. Thank you so much. I appreciate it.
Sure, anytime. See you later.
Bye.
And Professor, you said for both the homeworks and the exams, we can log in and out of them without any penalties, right?
And you can also change any of your responses if you want to, as long as you haven't submitted them. You have to submit them
Okay.
by the deadline. Okay, so for the kinetics homework, it's not due till Valentine's Day. So you have a lot of time to look at that homework and submit it twice.
Okay, sounds good. Thank you.
Yeah, the homework is really there to help you. It's not to hurt your grade or anything. It's to help you keep pace with the class and understand the concepts. All righty.